Firstly, background to the research study. Purpose: the study focused on the understanding the freeze-thaw effect on the creep behavior of crumb rubber concrete CRC. This is crucial method for the safety and durability of road pavement in a very cold area. Problem addressed: the amount of used tire is rapidly increasing worldwide and poses a challenge to the environment. Conventional disposal methods such as landfill and incineration are harmful, so incorporation rubber particles into concrete is a sustainable solution. Aim of the research: investigate how freeze-throw cycle affect the compressive strength, creep behavior, and dynamic modulus of elasticity of CRC. Develop a prediction model for the creep failure of CRC under the freeze-throw condition using well-bull distribution. Significant: the study aimed to improve CRC application in road and bridge construction, especially in coal region, which promoting environmental sustainability through the recycling of used tire. Secondly, identification of the most important material used in research. Name of material: chrome rubber concrete (CRC), which contain rubber particles from used tire. Composition: rubber particles made from scrap tire, replacing 10% of the volume of fine aggregate. Particle size: 3 to 6 mm. Cement: ordinary Portland cement PO 42.5. Fine aggregate: river sand with fineness modulus of 2.8. Coarse aggregate: crushed stone, grain size 5 to 20 mm. Additive: clash 1, fly ash and high performance polycarboxylic acid water reducer. Manufacturing process: mixing: rubber, gravel, sand, fly ash, and cement are mixed together and stir for 60 seconds. Curing: the mixture is filling into mold and stored in curing box at 20 Celsius and 95% humidity for 38 days. Properties: CRC exhibit good frost resistance, ductility, and energy dissipation. However, replacing sand or stone with rubber weaken the compressive strength and modulus of elasticity due to low stiffness of the rubber and weak interfacial adhesion. Application: suitable for road construction in cold region due to high freeze-throw resistance and potential use in energy-absorbing and soundproof structure. Reason for selection: rubber particles improve frost resistance and sustainability of material, overcoming both environmental and technical challenge.
Methods for developing sustainable materials. The research paper focused on the use of chrome rubber concrete (CRC) as a sustainable material developed by incorporating rubber particles derived from waste tires into concretes. Here an explanation for development of the sustainability materials. The first one, material composition. CRC is created by replacing 10% of the fine aggregate sands with rubber particles from recycled tires. These particles range in size between 3 to 6 mm. Number two, material properties. The rubber particles improve sustainability by reducing environmental impact from waste tires. CRC shows properties like better frost resistance, energy absorption, and reduced mass loss under freeze-thaw conditions. Number three, mixed propulsion. The concrete mix includes cement, sand, crushed stone, water, fly ash, and a water-reducing agent. Rubber particles are evenly integrated during the premixing process to ensure uniform distribution. Number four, curing. The specimens are cured at 20-degree temperature and 95% humidity for 28 days to ensure proper material strength. Types of tests conducted on the sustainable material. Number one, compressive strength test. Compressive strength test measures the strength of CRC after subjecting it to various freeze-thaw cycles: 30, 60, 90, 120, 150 cycles. A cubic specimen is loaded until failure to observe the reduction in strength due to freeze-thaw degradation. Number two, initial creep test. This test evaluates CRC's long-term deformation creep behavior under different stress level ranging from 40% to 90% of its compressive strength. Specimens are subjected to constant stress for extended periods while recording strain to observe creep damage and failure. Number three, dynamic elastic modulus test. The dynamic elastic modulus is monitored as it decreases with increasing freeze-thaw cycles. It's assess CRC stiffness degradation, which is critical for understanding structural reliability. Spelling and mass loss measurement. Observation of surface damage and spelling quantify the degree of physical degradation under freeze-thaw condition. Number 5. Microstructure analysis (SEM) test. Scanning electron microscopy (SEM) is used to examine the internal structure of CRC. The test highlight cracking, pore development, and the interfacial debonding between rubber particles and the concrete matrix. Number 6. Creep damage model. A Weibull probability-based model is developed to predict creep failure behavior under freeze-thaw cycles. It provides reliability assessment for CRC in cold climates. So, in summary, CRC is developed as a sustainable material by incorporating recycled rubber particle, and it undergoes rigorous testing including compressive strengths, creep behavior, dynamic modulus, microstructural analysis, and predictive modeling. These methods ensure its durability and practical application in cold environments. Thank you.
Analysis of results from tests performed. Analysis showed replacing 10% of fine aggregate with rubber particles in symphotic concrete affects the creep behavior of concrete after the freeze-thaw cycle. The tests performed include the measurement of compressive strength, uniaxial creep, and dynamic elastic modulus. Compressive strength identifying concrete resistant to compressive loads. Uniaxial creep measures the tendency of concrete to undergo permanent deformation under sustained stress. For dynamic elastic modulus, evaluates the strength and elasticity of a material under varying conditions. Results from 30 to 150 freeze-thaw cycle provide insight into the durability and performance of rubber concrete in extreme conditions. Sustainability concepts reduce, reuse, or recycle. The use of rubber particles, which are produced from recycled used tires, complies with several sustainability concepts, namely reduce, reuse, and recycle. First, reducing material used by utilizing waste tires as aggregates in concrete, the use of new raw materials can be minimized. Second, reuse. The process of processing used tires for use in concrete is an example of reusing materials that are traditionally considered waste. And third, recycle. By recycling tires, not only does it reduce the volume of waste, but it also improves the mechanical properties of concrete. In conclusion, this study has the potential to improve sustainability in the construction industry, especially in cold regions, by utilizing resources more efficiently and reducing environmental impact. The trip damage model, based on the Weibull distribution, also represents a better approach to understanding and predicting the failure of rubber concrete, important for Practical applications in road engineering.
Implementation of sustainable materials addressing waste management challenge. Waste tire accumulation is growing global concerns, with billions of tires projected to require disposal by 2030. Traditional disposal methods such as landfilling, burning, and using tires as fuel result in significant environmental harm, including air, soil, and water pollution. By justification, incorporating waste tires into concrete offers an environment-friendly alternative to these disposal methods. By recycling tires into chrome rubbers and using them as a partial replacement for fines aggregates, the study aligns with sustainable development goals and promotes resource efficiency. Enhancing concrete's property. The freeze-thaw resistance of concrete is critical in cold regions where temperature fluctuations cause significant damage, including spalling and strength degradation. Chrome rubber's low thermal conductivity and elasticity make it an excellent additive for mitigating these issues. For justification, the study demonstrated that CRC can resist severe freeze-thaw conditions better than conventional concrete. Rubber particles absorb energy and accommodate thermal deformation, reducing cracking and improve durability. Sustainable engineering practice. Construction industries are seeking sustainable materials to reduce the carbon footprint and reliance on renewable resources. CRC integrates recycled material while maintaining the structural integrity required for engineering applications. For justification, the research validates that CRC, despite minor reductions in compressive strength, offers acceptable mechanic performance and hence durability. It provides a dual benefit of waste recycling and infrastructure longevity, making it a sustainable choice for pavement and cold region engineering. Technical feasibility. Chrome rubber's particle 3 to 6 mm were used to replace 10% of fines aggregates in a C14 grade concrete mix. Surface treatments and optimized mix preparation were implemented to address potential strength reductions. Justification. Experimental results show that treated rubber's particle improve the bonding between the matrix and aggregates, mitigating weaknesses and maintaining mechanical properties under cycling freeze-thaw conditions. Conclusion of the research study. Achieving sustainability in material usage. Objective. Explore the potential of using chrome rubber from waste tires as a sustainable material concrete. CRC demonstrates its ability to repurpose waste rubber effectively, reducing environmental harm from traditional disposal methods. By replacing 10% of fine aggregates with the study aligns with sustainability goals while ensuring functionality in structural application. Evaluating freeze-thaw resistance. Objective. Investigate CRC's durability under cyclic freeze-thaw conditions. CRC showed a mass loss rate up to 11.2%, a compressive strength reduction of 6.51% until 47% after 13 until 115 freeze-thaw cycle. Despite these reductions, the material exhibit better durability than conventional concrete due to the elastic and thermal properties of rubber particles, which mitigate damage from thermal expansions and contractions. Analyzing creep behavior. Examine the long-term creep characteristic of CRC under various stress level and freeze-thaw condition. CRC exhibits distinct creep behavior with critical stress level determining failure threshold. The study revealed that CRC could withstand stress level below 15% of its compressive strength without failure. Even after 115 freeze-thaw cycle, the Weibull distribution-based creep damage model developed provides a reliable framework for predicting predicting CRC's long performance. Understanding microstructural change. Identify the mechanism behind CRC performance under freeze-thaw conditions. Microstructural analysis revealed that damage primarily occur at the interface between rubber particles and the cement matrix, with increased porosity and crack propagation over successive freeze-thaw cycles. The finding highlight the importance of improving the rubber matrix bond and its performance. Engineering application. Objective: establish CRC's feasibility for practical engineering application in cold regions. The studies confirm CRC sustainability for instruction subject to harsh environmental conditions such as road and bridge. The material's durability and resistance to freeze-thaw damage make it a viable alternative to traditional concrete, particularly in sustainability-focused projects.